Yes.
Isn't negative 5 squared also 25? Oh, but the square root can only be positive?
When you check it, oh yeah, when you just have the root like that, it's just the positive. It's when you take the root on both sides that you get plus or minus. All right, exams are over here if you want to pick up your exam. All right, let's talk about the exam real quick. I'm going to turn the lights down a little bit, a lot of bit, so you can see how the class did. So this is the distribution of A's, B's, C's, D's, and F's. We had 6 A's, 6 B's, 7 C's, 2 D's, 4 F's. This is the actual exact grades from highest to lowest. So the highest grade in the class was a 96.4. The orange line there is passing, right? So you can see how many students passed the test. And then down to 25, there are 25 students that took the test. So your exams are right here, sir. If you want to grab yours out of there. So that kind of gives you an idea of where you are, like relative to the rest of the class. The average on the test. The average on the test was a 74.9, 75, all right? So X bar is what we use to represent the average. X bar was, let's say 75%. So the average score was 75. And then the standard deviation, which we represent with this sigma, was 17.8. And that number, 17.8, just tells us like how far apart the grades were from one another. The bigger this number is, the more spread there is. So like if this number gets really big, then that means you have like a lot of A's and a lot of F's and not much in between. The smaller this number is, the more clumped together everyone is. So I know that number probably doesn't mean a lot to you, but this is about what I see in most math classes. About 17, 18 is standard deviation. So everything looks pretty normal, I guess. In the sense that the class average was a 75. So one of the misconceptions in college, I think, is what an A is, what a B is, what a C is, what a D is, what an F is, right? So what does a C mean in college? 70. Yes, that's the range, but what does it mean? What is it supposed to mean? Passing, yes. Average, okay? A C student in college is an average student, right? B is above average, A is exceptional. Now I know everyone here wants a 4.0 and everyone wants to be exceptional, right? But when the class average is average, then I'm okay with that, right? What I don't want to see is the class average being like a 60, and then it's like, okay, the average student's way below what average is supposed to be. Does that make sense to you? I know it doesn't help you. I mean, like you don't like a C, I get it, okay? But this does not alarm me. Okay, in terms of this average. Let me talk about how I computed your grade. Let me see how many questions there were. There were 11, right? I did not even grade number 11. Everybody got credit for it, no matter what, okay? So that's like, if you did it right, then good. If you did it wrong, it didn't hurt you. So that's like a built-in curve, right? So it was, every problem is worth 10 points. Which means since there were 11 problems, there were 110 points possible. Not that you could get over 100 on the test, but your grade is out of 110. So let's say you go through here and you see that I marked off minus 30, right? The way I'm going to calculate your grade is I'm going to take 110, I'm going to subtract 30 from that, which is 80, and then I divide that by 110. And that's going to give me a decimal. And that I convert to a percentage, all right? So if you got 110 out of 110, you got 100 on the test. Make sense? If you're trying to figure out like, hey, he took off 5 points, but my grade's not a 95. If you're trying to figure out why that is, that's why it's that way. Questions? If you have specific questions about why I took off, you know, what happened here, why did you take off 2 points, like why did I get this wrong, that's a conversation that we can have at another time. All right, either during my office hours before class, or you come into my office hours later on in the afternoon, or you can call me or text me and we can talk about it, all right? How do y'all feel about things? Y'all all right? Yeah? So remember, there's no makeup tests, there's no test corrections, right? This is a college level math course, STEM major math course. So I told you on the beginning, I want you all to come in, be prepared on the day of the test, for the test. But at the same time, if you did not do well, I don't want you to be like, okay, it's all over, all right? If you were at the tail end of this, these grades here, and the rest of the semester goes really well for you, and you're on the other end, then I will always take into account that maybe you just had one bad test, all right? And that will go for everybody here, all right? That goes for everyone. I want to kind of preface that with, I'm never going to offer one student in this class something I don't offer everybody. So if I decide to say, hey, we're going to drop the lowest test, if I ever say that, it will be for everybody. It won't be for one person, right? Okay, so, but right now, as it stands, no tests are being dropped. You know, it is what it is, all right? Because I don't want to, I want you to like, if you're freaking out about your grade, I want you to freak out because I want you to like do something to get yourself more prepared for the next test, all right?
Yes.
Okay. Anything else we want to talk about? They're on the syllabus. They're on the syllabus, so just check that out. And they're in the morning, though, before this class. All right. And then later on this afternoon. All right, how do I turn this thing off? Disconnect. Disconnect. And then I'm going to turn this off. All right, so today what we're going to do, as soon as I put it up on the, I'm going to use that screen over there for today's notes. We're going to do two things today, two sections. We probably won't finish the second section, but we're going to try to get as far as we can into that second section. So the first section we're going to be covering is 3.5. Where'd it go? 3.5. There it is. There it is. Okay. Why is it behaving that way? What's going on? It's acting weird. Well, let me try something. Technology does not want to cooperate with me today. See if this makes it any better. All right, looks a little more stable. All right, so 3.5, graphing techniques and transformations. I'm just going to put tech transformations. So hopefully you remember that we talked about how many different functions you're supposed to know what they look like, those toolbox functions. Do you remember? It's like 8 or 9. I think it's 9. We had like the identity function, the squaring function, the square root, the cube root, the absolute value. Remember that greatest integer function that looked like steps, right? All these different functions that we're supposed to kind of know what they look like, right? And this section is about how we can take those functions and make some small adjustments to them and how that transforms the graph. And so I think this section most students do pretty well with, all right? And there's a good summary at the end of this section in the ebook that summarizes everything that's here in notes. Okay, it's right there, or it's right here. Now, I'm not going to go through this like line by line. I'm just going to do it on the board here, and I'm just going to kind of do a quick summary of what's going on. So I'd like to start with an example. I think sometimes an example is the best place to go. So let's start with this function f of x equals x squared. All right, everybody in here should know what that graph looks like, right? Without having to think too hard. That's one of the ones that I put up on the board. It's called the squaring function. It starts here at 0, and it looks like this thing called a parabola, right? That's x squared. So let me ask you what would happen if I change that function a little bit. So what does this look like? Question mark. So I'm going to do a couple of parts here. Part A, what would that function look like if I added 2 to it? In other words, what would happen if I took x squared and added 2? What would happen? Move the whole graph up 2. That's what would happen. You just take this whole picture and move it up 2. And that's called a transformation. We're taking something we know and we are transforming it by shifting it up 2. So this plus 2 right here, right, has the effect of moving it up 2. Right? Up 2. All right, so now my graph would look like this. I go up 2. That's where I put that dot. I go up on the left, up on the right, like that. We're just trying to get a quick sketch. We're not trying to be perfect here, okay? Later on today, we're going to be graphing quadratic functions, and we're going to have to be very precise with our graphs. This is just to get like a ballpark idea of what's happening. Okay, good? What if I tell you to take f of x and subtract 3 from it? What do you think that's going to do? Move it down 3, right? Pretty simple idea, right? Take 3, subtract, you're going to go down 3. So the picture will look like this. 1, 2, 3, put a dot, and then make it go like that. So this is, I think, hopefully you agree, this is a pretty simple idea, right? But for each of these, remember that we can ask all those questions like number 10 and number 11 on the test, right? What's the domain? What's the range? Where's this increasing? Where's this decreasing, right? What are the intercepts? All those questions are still in play, right? Let's just do that real quick. Let's do domain and range on these real quick. What's domain? All real numbers. Range? 0 to infinity. Okay, domain. All real numbers. Range? 2 to infinity, right? Domain? All real numbers. Range? -3 to infinity. So everything we've done is still in play, right? Okay, now, let me do some of this. We're going to still stick with this function right here, all right? C. Part C. What does this look like? Okay. Notice the notation here. I've added 2 again, right? But where's that 2 being added? Inside with the x, right? I didn't write it this way. Part A was this, right? Part A was this, and everyone said move it up 2. But now I'm saying plug the 2 in, add the 2 inside with the x. So what does that look like? So it's not this, right? What does that look like here? Where the x is, you add the 2 before you square it. You see? You're not squaring x and then adding 2. You're adding 2, then squaring. See the difference between those two? How does that impact the graph? What does your instinct tell you? Like, you probably already know, okay? But what does your instinct tell you?
Left or right?
It's going to go the other, like, if the adding 2 and subtracting 3 like this just moved it up and down, then this should maybe move it left and right, yeah? And that's correct. And most people would think that if you add 2, it should go right 2, right? But it's opposite. When it comes to left and right shifts, it's opposite of what you would think. Okay? So so I need to put it here, what's happening. This right here tells me I'm going to go which direction? Left 2. And then right there, that means left 2. So let me draw the picture. I'm taking this point right here, that was here, right? And I'm going to move it to left 2. 1, 2, that's -2. There it is, and then it continues and does the same thing. So why is it opposite? Let's see if we can't figure that out real quick. or not figure it out, but let's convince ourselves. Right here, this point, right at the beginning is 0, 0, right? And that comes from the fact that if you plug in 0 here, 0 squared is 0. Agreed? Okay, right here, if I plug in 0, what happens? 0 here, what's 0 plus 2? 2, 2 squared, 4. So at 2, I'm supposed to be up at 4, right? What happens at positive 2 over here? 2 plus 2 would be 4, and then squared would be 16. Do you see it? Positive 2, you'd be way up there. Not at 0. So if you thought that it was going to go to the right 2, do you see that it wouldn't work? But if you plug negative 2 in, what happens? Negative 2 plus 2 is 0, right? And 0 squared is 0. So what happened was this point that was here now moved to the left 2. Opposite of what it looks like it should do. Understand? Okay, what about this? What would this look like? F of x minus 3. In other words, this time we're taking away the 3, right, inside with the x. So I'm taking the x, I'm taking away 3 before I square it. So that's going to be a shift left or right? Right, by 3, right? This is a shift right 3. Same thing here, right? Okay, so my graph looks like this. 1, 2, 3. There we go. Okay, these are called horizontal shifts. The first two we talked about, the up and down, are called vertical shifts. These are horizontal shifts. Vertical shifts are exactly what you would think. If you add a number, it goes up. If you subtract a number, it goes down. Horizontal shifts are opposite of what you think. If you add a number inside, it goes to the left, right? And if you subtract a number inside, it goes to the right. All good? Okay, so I'm going off this table here. This is where I say they review this. They use the number k here for that number that I'm adding and subtracting. This was the vertical shifts, adding k, subtracting k. They use h, I don't know why. They add h inside, subtract h inside. See the difference in the notations. All right, continuing. Let's do part E. What if I take this function and I multiply it, let's say, by 4? In other words, I take that function and I put 4x squared instead of x squared. So I'm multiplying the function we know by the number 4. Well, that does not move your function up or down or left or right. That has the effect of what we call compressing or stretching the function. So this number right here, what you have to do is you have to look at it and look at its absolute value, all right? So look at the absolute value of 4. What's the absolute value of 4? 4, right? If this number, if this is greater than 1, then you're going to, then it stretches vertically. What do I mean by that? This one's harder to show, okay? So what I'm going to do is I'm first going to graph this one. This is x squared. Now I'm going to show you what 4x squared looks like. What it does is it takes this graph, and it's like you grab these two ends and you stretch it up by a factor of 4. And so it pulls the graph up, but it doesn't move it. It doesn't move the graph. It just makes it more, how could you say, narrow?
It increases like faster.
It increases faster, exactly. 4 times as fast. So it stretches up. So like if this number, if you plug in here and you get a number, an output on this one, the output here is 4 times bigger. Whatever output's here, the output on the other one's 4 times bigger. So it looks like we stretch it. That's what it visually looks like, okay? That's if this number, if the absolute value of that number is bigger than 1. What if it's less than 1? Let's try that. So it won't stretch it vertically. It'll actually stretch it horizontally. It'll go the other way. So there's different ways you can say this, but I'm just going to say stretch horizontally. Okay, so let me give you an example. F. If I do, let's say, 1/4 times f of x, which in this problem would be 1/4 x squared, then I take the absolute value 1/4, right, which is 1/4. That's less than 1, and that means it's going to stretch horizontally. So if our original picture looked like this, then 1/4 x squared would stretch it this way, which means it would go more like this now. And I'll be the first to admit that when it comes to stretches, they're hard to graph because it's hard to be precise. When you move a graph up or down or left or right, that is, up 2 is up 2, right? Down 2 is down 2, left 2, right 2. But stretching is a little bit more subjective. Yes?
So how do we get it precisely?
We are not trying to get it precisely. We're just trying to, we need to make sure that we know that it's different than the original, right?
Okay.
How much it's different? Well, you know what? If we really wanted to know, we just go to a computer and have it graph it for us, okay? By the way, does a stretch change the domain? Stretch has no impact on the domain. How about the range? Stretching does not impact the range. Okay? Just something to note. This still has a domain of everything, right? And the range is from 0 to infinity for both pictures, right? So stretches do not have zero impact on domain and range. All right, continuing. We still want to stick with this. So we've got vertical shifts, horizontal shifts, and stretching either vertically or horizontally. Okay, those are the things we talked about, right? Next thing we want to talk about is what if I put a negative in front of the function? So I'm on G here. So what if I put a negative in front of the function? Like for this one, what if I put a negative in front of x squared? What would that look like? What does a negative in front do? What does that do? Well, everything that used to be positive is now negative, right? And everything that used to be negative is now positive. So that has the effect of taking every point that used to be up on top and putting it on the bottom, right? Or if there was a point on the bottom, it's going to move it to the top. So what is that? Flips it over what? The x-axis. So this is called reflection about the x-axis. So I'll show you the picture again. If our original function looked like this, if this is x squared, then negative x squared is that, right? Just reflection about the x-axis. Is that right? Okay, let me give you another one of those. What would negative 4 times the function be? And so for this example, what would negative 4x squared do? So you flip it, right? The negative has the effect of flipping it over the x-axis or reflecting over the x-axis, but what does the 4 have the effect of doing? Stretching it this way, right? So this is like 2 in 1. This is going to be, did that already turn off? Oh, that's my laptop. It's not plugged in. Hold on. I don't even think I need this right now, but okay, so this is going to have the effect of taking our original function, x squared, right? That's x squared. It's going to reflect it and stretch it. So it's going to look like this. Sometimes people will call vertical stretches, they'll call this vertical stretch. Instead of calling it vertical stretch, they'll call it a horizontal compression, right? Stretching it vertical is the same as compressing it horizontally. So you might see that like in a calculus book or something. You might hear some different terminology.
I thought it was vertical stretch, vertical compression when it's like, when it's less than one.
If you stretch horizontally like this, you could call that a vertical compression. So it's kind of, I'm not going to say compression in here at all. I'm just going to stick with what did I say, stretching, right? Stretching vertically or horizontally. All right, so recap. We can go up, down, vertical shifts, horizontal shifts, right? Stretches vertically, stretches horizontally. We can reflect, right? We can reflect over the x-axis. Any questions? Okay, this one's going to be a little bit tricky. What if I do this? What if instead of me putting a negative in front of the function like that, instead of me doing that, what if I put the negative on the x inside the function? So what if I put the negative on the x before I square it, right? Before I square it. That's reflection over the y-axis. Good. That's reflection over the y. So when you put a negative inside here, that's reflection over y. Now, for this particular problem, does anything change? If I take my original x squared function right here, and I ask you to reflect it over the y-axis, does anything change? It's the same exact function, isn't it? For this one. Not every function, this will be the case. But for this particular function, it's the exact same function. Right? So if I reflect it, right, it lands right on top of itself. Hey, that's also called being what? Even, right? An even function when that happens. Okay, let's see if we've got it all here. Yep, okay. We're ready to do some examples. Now I'm going to be, for this first few examples, I have to be somewhat precise in my drawing. So this example, what I'm going to say is this. Find the function. All right? In other words, here's what I'm asking for. Give me what the algebraic expression is for the function I'm about to draw for you. Okay? I'm going to draw a function, and I want you to tell me what that function is. All right? So here it is. 1, 2, 1, 2, 3. What is that function? Oh, hold on. I want volunteers, because. So raise your hand if you. Okay. So can you talk me through it?
I was just going to say it's a square root.
It's the square root function. Okay. You have to know that first, right? So you know this is the square root function. Everyone agree? Okay. So this is. We look at that. Here's what we know so far: that this function is a square root function. Now, this is not right, because if I did that, it should start here and go like this. How do I know that? We studied that, right? Okay, continue.
So in order to get up there, you probably have to...
To get up here, you have to what?
Probably add...
You have to add... No, you're right. Right? Up and down shifts are just what you think. You'd have to add 3. Okay, but we also have to go to the right, too. And that's opposite of what you think. Right?
Also subtract, right?
Subtract how much?
By 2.
Subtract 2, but then we also have to add 3. Y'all with me? Subtract 2 and add 3. But where do we do it? Well, left and right shifts are opposite of what you think, so we have to subtract 2, but where? Out here? Like -2 out here? Or inside the root? Inside the root. The left and right shifts happen inside the function next to the x. So I'm going to write this down. This right here, let me I don't think I have enough colors for this. Yeah, I don't, but, oh, here's some colors. Let me do it this way. So this right here, ooh, that's a good green. That's just that function right there, right? That's what that is. Now, if we take the square root and we put x -2 like that, that is a left and right shift because the -2 is inside the root, in there, right, with the x. That's going to go opposite of what I think, so that's going to move to the right too, isn't it? So it's going to take this picture that we just drew in green, and it's going to move it to the right too, which puts us here. Okay? And then, what? Add 3, right? We want to add 3 to move it up 3. So we take this right here that we just had, and we add 3. And that should take us, take that picture in red, move it up 1, 2, 3, and that's this, right? Do y'all see it? So this is our answer, right? This is our answer right here. Now, you have to recognize that as being the square root function, right? If you don't recognize that as being the square root function, this isn't going to happen, right? Questions? Let's do another one. Same thing. What's the function? This was our answer, right? This is our answer. Okay, so let me draw again another picture for you. All right, so let me just leave this same thing up here. -1, -2, -1, -2. How about this picture? And again, I want to volunteer. I don't want people just telling me. So here's the picture. Do you want to try?
I want to give it a try.
Okay.
I would like to.
Well, tell me first. Do you know what the function is?
I think it's an absolute.
Absolute value. Everyone agree? This is an absolute value function. I agree because it's a v, right? A sharp corner. Okay, good. Let me write that down first. So if we just did the absolute value of x, that would look like that right there would just look like this v right here, right? That's what the absolute value of x will look like. Okay, continue.
It's a reflection about the x-axis.
It's a reflection, right? So that means you need to do what?
You need to put negative outside of the absolute value.
In front, right? Not inside, right? So taking care of the reflection. Everyone got that? If we do this,